Hello everyone, this is Frank. Welcome to this series of lecture, Anatomy of Pytorch XLA. In this series of lecture, we're going to talk about what is Pytorch XLA and why does it exist. And also we're going to have an in-depth understanding of how it works internally and how can we use it. Without further ado, let's jump into the content. So the first part is that let's take a look at the standard Pytorch execution model. We call that eager execution. So what is eager execution? As implied by the name, in the eager execution model, when you write a line of Pytorch code that performs an operation, that operation happens immediately. The result will be computed and available right away. So below, I give a very simple Python code. So here A equals to a random matrix, and B also equals to a 2x2 matrix. So here on the third line, we have a C equals A plus B. So when we add this third line, the Pytorch will compute the value of C immediately. So how it works internally. Pytorch will send instructions for each individual operations one by one to GPU or CPU. In this case, it will send this addition operation when it's hit the third line right away. There are many good sides about the eager execution, including it's easier for debugging. But what's the downside or what's the problem of the eager execution? When we have a hardware accelerator, specifically TPU or GPU, the eager execution actually performs very inefficiently. For example, GPU and TPU are designed for performing potentially thousands or millions of computations simultaneously. Their architecture is optimized for large fused matrix operations instead of running many small independent operations. Think of them as a highly specialized factory built for bulk processing. So for the eager execution tends to send many small individual commands to the accelerator. It's like telling a factory, first make a screw, then the factory makes the screw for you, and then wait for the next instruction, and then you say make one knot. Then the factory will prepare for making a knot and then make a knot for you. And then you give the final instruction saying attach the screw to the knot. And then the factory will prepare for that operation and do what you instruct it to do. This is very inefficient and hard to perform in parallel. It will be way more efficient for you to just tell the factory that I want to make a screw, a knot, and attach them together. So the problem of this model is that first, there is a kernel launch overhead. There is a fixed cost for just starting any operations on the accelerators. Launching thousands of tiny kernels means that you spend a lot of time paying those overhead costs rather than doing meaningful and useful computation. Also, there is underutilization problem. The power of the accelerators might end up just wait for the next small command, failing to reach its peak computation throughput. So what we need is a way to describe a large chunk of computations to the accelerators all at once. This allows the hardware accelerators to optimize the entire sequence of operations rather than execute them inefficiently piece by piece. Let's take a look at what is XLA. So the XLA is a domain-specific compiler for linear algebra operations developed by Google. So here are two keywords, domain-specific and compiler. Domain-specific means that XLA isn't a general-purpose compiler like GCC for C++. It's highly specialized for the types of mathematical operations common in the machine learning area. And a compiler means that it's a translator. It translates the code from one form to another. In this case, it translates the code or your model that's defined in Python to a low-level machine learning code that hardware can understand and execute directly. This project is open sourced. You can find its GitHub page here. And on this page, it has this graph to tell you what the XLA does. So on the one side, It's the common machine learning frameworks such as TensorFlow or Pytorch. And on the other side, it's the hardware that you can run your machine learning models. So the OpenXLA project can translate the model that you define in those high-level frameworks like TensorFlow or Pytorch to a high-performance execution code across different hardwares. So the core idea of XLA is to build a computation graph. It analyzes the whole graph before executing anything. The benefits of doing so include operator fusion, buffer analysis, and target-specific code generations. Operation fusion is simple to understand. It combines multiple individual operations into a single, more efficient, optimized kernel. For example, if you have a for loop in your model that will iterate 10 times, XLA actually provides a scamp kernel that will run this for loop more efficiently. And this addresses the problem that we just discussed. Instead of sending many independent kernels to your accelerator, Operation Fusion allows you to send a single, more efficient, optimized kernel to your accelerator so that it can perform much faster. Also, having the idea of your whole computation graph allows XLA to intelligently manage your memory allocations and reuse or potentially reduce the overall memory footprint. XLA compiler can optimize specific for your accelerator. For example, it has special passes that optimize for GPU or TPU. Besides, you can also write your code once and run on different accelerators and hardwares without changing your code or knowing the details about your hardware. Now you must think, it would be awesome if Pytorch and XLA can work together. Pytorch XLA is a package that acts as a bridge between the Pytorch front end and the XLA compiler backend. Remember that Pytorch is very easy to use, but it has eager execution. However, XLA needs the whole picture. It needs a computation graph. The challenge is that, how do I get the computation graph while Pytorch is on its eager model? We will discuss more details about how the Pytorch XLA achieves that, but for now, let's have a very high-level general idea on how it works. First, you define your Pytorch model mostly as usual. Then you introduce XLA package to your project, and it uses special mechanism to intercept the Pytorch operations. We will discuss more in details about this mechanism in the next lecture. For now, you can just believe that it changed your Pytorch behavior. Instead of executing immediately, Pytorch XLA record all the operations and build the XLA computation graph based on your code. Then this graph is passed to XLA compiler for further optimization and optimization specifically for your hardware. XLA then optimizes and compiles the graph into a high-efficient code for your target accelerator. Then the optimized executable is sent and executed by your hardware. It sounds like a very simple process, but it involves a lot of details. In this series of lectures, we'll take a deeper look on how it achieves this internally. Now we have discussed about why we need Pytorch XLA and what it is. During our lecture, I keep mentioning that one of the major reasons why the compiled version of the operation is more performant than the uncompiled operation is that it confuses many small operations into a large fused operation. So let's use a real example to demonstrate the time differences between many small operations versus a large fused compiled operation. This is a script that I wrote to demonstrate the time differences between many small operations and a fused operation. Let's take a closer look at our script. The first section is import section. There's nothing special there. Then we come to the set device section. In this experiment, we are going to run our script on both CPU and GPU to see if their results are agree with each other. Then we come to the define operation section. In this section, we define a simple function which has some matrix manipulation operations. So for example, we take a min And we also do some reduction, and we do the normalization, and then we have a multiplication and addition. So those are the very common operations that we can do to matrix. So this will represent a very simple chain operations. Then we come to the compile section. Notice that we have our separate operation and a compiled separate operation. We will run both of them to see if there are any time difference between the uncompiled version of the function and the compiled version of the function. So here are some core testing functions. So first we have our time operation function, which takes a function, the argument to that function, and how many times the function need to be run. We have this because we will take the average of the running time, so it will be more stable. It's important to notice that before the actual timing section, which is below, we have a warm-up section here. So the reason we want to have this section is that we want to ensure the compilation overhead and the initial GPU kernel launches are not included in our main timing loop, which is down here below. Then we have our run experiment function, which it takes a tensor shape and will create 3 tensors based on the tensor shape. Then we will run the timing function for the separate operations and compile separate operations. We will compute the ratio. We will compute the ratio between the uncompiled version and the compiled version. Finally, we return this ratio. The last section is run experiment section. So here we're trying to run our experiment using different tensor shape. Now let's run our experiment. So first, we'll clear all the result, and then we run it all. It will take some time, and now it's run the first loop. We have a 1 by 1 matrix, that is 2 by 2, 4 by 4, 8 by 8. So here we graph our result. The x-axis is the exponential and the y-axis is the acceleration ratio. Basically is the time that's used by the uncompiled version versus the time used by the compiled version. We can see that at the very beginning, when the size of the tensor is very small, we don't get any significant increase for the speed. But as the size of the tensor increase, we see a significant gain of the speed. So this verifies our understanding that computing a large fused matrix is more efficient than computing many small matrices. Let's run the same script on the GPU to see if we get the similar result. In this experiment, I'm using Kaggle. In the session options, here we can change our accelerator to GPU. Kaggle is actually pretty good because it provides free GPU and TPU time, so it's a good testing platform for us. After selecting the accelerator, then we will say, then it terminates the previous session, so we can directly run all. Then it will start a new session with GPU support. Now it's running. And we can expect here, saying that it can found CUDA, which means it can found GPU, and it will run the test using GPU. Let's see. Yes, we're using device Tesla T4. Now we run the same thing. Keep running, keep running. Well, we can see that TPU is actually runs much faster than we see the result. But there isn't any performance gain using the compiled version of the function. Actually, in the most of the time, the compiled version of the function runs slower than the uncompiled version because the acceleration ratio that we defined above below 1. So why? What happened? This is a little bit beyond the scope of our lecture. To put it short, the reason why the compiled version of function is slower than the uncompiled one, especially on GPU, is that the Python standard eager execution on GPU is already use extremely fast and hand-tuned CUDA kernels. It's often difficult for the general purpose compiler to surpass those hand-turned, highly specialized, and highly optimized kernels that's provided by CUDA. So Pytorch has very good integration with CUDA. Compiling the function actually prevents us use those highly optimized kernels. Then you must ask, the most of the trainings nowadays are happen on GPU. If the eager execution of the Pytorch is already being highly optimized, then why do I want to compile my code? So the problem relies on our function here. Even it covers most of the common operations here, it's still too simple. A real-world neural network will be much larger and more complicated than this. In that case, the compilation will actually make the difference and run faster. Give me some time. Let me make a more complicated function to see if the compiled version will surpass the uncompiled version. Okay, welcome back. So here is a more complicated function that I made for this experiment. So here I call it complex feed-forward network-like module. So it has more complicated operations like this matrix mutation, and it has a sigmoid to introduce some nonlinearity. So it's more complicated. In the compile section, let's compile this. Here we have compiled complex feed-forward equals to torch compile function mode equals default. Alright, and if it failed, it will say compiled this equals to this. Alright, so in the timing function, we don't change anything. And in the run experiment section, we will have more change here. Let's first define our inputs here. And then we change here. Yep, then we have here, and instead of having a tensor shape, we will have a hidden layer size. We will have our hidden dimension here. All right. Okay. And we want to change our function under test to this. And compiled. Fast forward. That's it. Let's restart and run again. Okay, so we make sure we are Tesla 4, T4, and the size. Oh, because here the input is wrong. So we don't have this. We are going to have n here. Okay, yeah. So now we actually see some positive gain, and as the size increase, we see a larger and larger gain. Oh, actually, it decreases. Then we can see this a nice bell shape. Well, so I think this is understandable, because what the compilation saves is the kernel launch overhead, but when the tensor size is bigger and bigger, more and more time will be used for the actual computation. So the time that we saved from the kernel launch will be less and less significant. But anyway, this more or less demonstrates us that the compilation actually saves some time. A large fused operation is actually runs faster than many small operations. Okay, because this is a Pytorch XLA lecture, I'm thinking why not use the XLA compiler to compile our code? Remember that in our previous experiment, we didn't specify which compiler backend that we want to use to compile our code. The Pytorch actually uses its default compiler, which is Dynamo. So here we must specify the XLA backend as our compiler to use Pytorch XLA to compile our code. Right here, we don't need this line. Right here, we will specify the backend equals to open XLA. So by explicitly specifying the backend to use, the Pytorch compiler will use OpenXLA to compile our code. In order to use this OpenXLA compiler, we must include the corresponding modules. So the first is import torch XLA, which is the module name for Pytorch XLA. And we also want to import torch XLA dot core dot XLA module model as XM. Then in the set device section, we want to set our device to TPU. So Torch XLA provides a convenient function for us to select the TPU, our XLA device. Okay. So once we have our device, we will say if device.type equals to XLA. Then we want to do nothing. We can just print using device TPU. And we want to skip all the other sections. Okay, cool. After setting the device, and we don't need to change anything in our operation function. And here in compile, we already set the backend to OpenXLA. Here in the device type, we want to use so here when the device type equals to XLA, we want to call xm.markStep. This function will trigger the compile and actually run your code. Similar here. We will say xm.markStep. Cool. Okay, very cool. So we are done with our changing. Let's make sure we're using TPU, and let's run our code. Now it's loading XLA. We're using TPU. Keep running. Yeah, now it's running. We can see it's run really fast. And it's on device XLA 0, which is the only TPU that we have. Wow. So we can see the huge difference between the compiled version and uncompiled version. That is because, as what I said, the original function is fairly a complex function. Without the highly optimized kernels, this can run really slow. So the compile actually make huge difference, and I think this is a really good example to show you why we want to compile the neural network. Okay, let's summarize what we learned in this lecture. We learned that the Pytorch's default eager mode is flexible but can underutilize the accelerators due to the kernel launch overhead. And we also learned that XLA is a machine learning compiler that optimizes computation graphs using techniques like operator fusions for target hardware. And Pytorch XLA acts as a bridge that enables Pytorch users to benefit from XLA graph compilation on the accelerators with relatively minimum code change. Remember that we only change a few lines of our original code to enable it to run on TPU. Thank you very much for watching this lecture. Let's see you in the next lecture.